It is a great pleasure to finally be able to introduce Kristen Grauman. It has been a long time since we tried to lure her from Texas to visit us, and we have finally succeeded. Kristen is one of the shining young stars of computer vision today. She's done an incredible breadth as well as depth of work. I'm sure that most of you have heard of the pyramid match kernel. Maybe some of you don't know that this is Kristen's PhD thesis work, or part of it, I guess. Since that, she became a faculty at the University of Texas in Austin, where she has been doing tons of really cool stuff in a variety of directions. In fact, I think her output is overwhelming. I think she has more CVPR papers this year than all of CMU combined. So, which I think is. And Kristen has been working in a variety of directions, you know, unsupervised learning, the stuff she's going to talk about today. Just lots of very, very neat, novel ideas, and she has received lots of recognition for that. She has a career award, of course. She's a Microsoft New Faculty Fellow. She's a House Scholar Award from the Carell Institute, and the list goes on and on. And anyway, so we're very happy to get Kristen here. She unfortunately she will have to run off soon after the talk, but not before a PSR that in her honor is going to be Tex-Mex, I think. After the talk, you're welcome to go to the PSR, and Kristen will be there for maybe 15 minutes or so. So without any further ado, here is Kristen Grauman.
Okay, great. So thanks, Alyosha, for hosting the visit, and thanks to all of you for being here. I'm very excited to tell you about some of our recent work, and I'm going to talk about some work that's done mainly with my student Sudhinja Vijayanasimhan and also Sungju Huang. And I want to kind of tell you mainly about what we're doing to connect human intelligence to our visual recognition algorithms. And so we're motivated by the kind of fact of the fact today that we have many more sensors and much more visual data than we can. Nice, yes.
Sorry.
More visual data for me now, thank you. Okay. So many sources and so much volume of data that we're capturing. And as many of you well know, we can't yet make rapid index into or make rapid sense of an automatic means. So we're looking in general in my group at how do you automate recognition of objects and activities, and how do you search for visual content rapidly. And so just to give a taste of some of my favorite kind of motivating applications, what happens once we can treat visual data as fluidly as we treat other types of data today, such as text? So if we can make images and video naturally searchable, interconnected, we can pose queries that are really best expressed in a visual form. So something like this example suggests if there's something in the environment that you can maybe guess keywords for, but not so well, you can connect much more naturally with a visual query about the thing that you're interested in. We're also motivated by ideas for summarization. So if I'm looking at the discovery problem and trying to summarize content, say in long-running video, so that someone who's capturing this as some important data, say a primatologist who's studying these subjects, they can have a rapid view of what the content is without actually watching every frame. In the discovery world, we're also interested in how do you find the trends in the data, so things that even if you and I were to watch every frame, we might not be able to summarize well. And on the other side of that, look at what things are unusual. So detecting the novelty in these large collections. So again, we would know what to even look at. Okay, so these are just kind of motivating applications. Underlying all of these, I think, are fundamental recognition challenges. So how do we identify, categorize the objects in the scenes, the people, what they're doing, and the different categories of objects. Okay, so basically I'm going to focus on this challenge, the basic recognition challenge, and how we can bring humans into the loop to tackle this in a meaningful way. Okay. And so I feel like many of you are already very well familiar with these challenges, but just to give a little more context for those who may not be. So the recognition problem itself is quite challenging because of all the variety as you see here. So we have to be able to be robust to the imaging conditions like the viewpoint, the illumination, the pose of these objects, and so on. And all of these can greatly affect the kind of image we get. Right? So even though these things are all of the same category, I want to be able to ignore these kind of nuisance parameters and still robustly categorize the objects. At the same time, we have these major scale challenges. Right? And that's what I'm going to touch on in a bit more detail today. So just think about the amount of content that's constantly generated in the world from any kind of sources. We have to have algorithms that are not only robust to these kind of variations on the previous slide, but also scalable to capture and very quickly process this kind of data. Okay, so we have the robustness challenge, the scale challenge. And these together sort of suggest that handcrafting models for every category of interest that we have, so for every activity or for every object category, is not necessarily, is certainly not the most practical thing that we can do. So indeed, much work is looking at how do you bring in statistical and machine learning techniques so that you can learn how to identify these visual patterns, learn to discover them. So what does that mean? So that means we're taking this very complex visual world, and then we'll annotate some data. So some human will make some labels on these examples, and then we'll come up with a classifier. So there's this natural pipeline that we're seeing emerge of some way to do this both robustly and in a scalable way, potentially. But I think there's a lot more attention that we need to spend right on this interface here. Right? So how we, as human annotators, are teaching these systems about the complex visual world. And that's the focus today. I want to talk about the problem of how to transfer human insight into our visual recognition systems, acknowledging some important challenges. One, the machine learning algorithms, as they stand, may not always be very accommodating for the kind of patterns and structures that we want to learn. So the kind of point and label mode. You know, I'm seeing this contrast between this great complexity and the fact that we're often trying to map these into binary classifiers that can give us, robust responses about the categories we care about. So this kind of mold may be restrictive. And secondly, human effort is very expensive. So if we're going to teach these systems through data, and we're still involved in terms of annotating the data, we want to be able to intelligently utilize the humans that are in the loop, right? So we spend efficiently. So what I'm going to tell you about today is kind of two parts. First thing I'll talk about is how we can do this learning in an active way. So how do we go back from the models that we have to the data that we see and ask good questions to humans so that we can refine our models well. And then in the second part, I'll talk about how we can listen more deeply to the humans that are responding to these questions. Okay, and that means looking a bit further beyond what we can superficially get from the kind of, say, image tags that we get from humans who look at image and describe them. So we can listen to some implicit cues. So first, let me sketch what's kind of the standard pipeline. What you would do if you're building an object recognition system today. You'd have a very happy annotator. And then you'd have some labeled data. So some data you decided that would get hand annotated for every category of interest that you're going to be able to predict. Now, you'll have these category models. You're willing to find then those objects in new images. And a couple things to note here. Oops. A couple of things to note here. One, that we knew what kind of data to put into this pool, and we knew how much. Usually we assume more is better. So the more things we could get humans to look at and describe for us, the better the models would be. And also note that this is sort of a one-time, one-pass process. You're going to make these models, you'll fix them, and they'll have the quality that they have from then on. But what we're proposing is to instead think of this as a continuous process. Right, so let this be an active visual learning pipeline that continues where even once I have some initial models based on that early data, we'll survey anything that's still unlabeled, partially labeled, and let the system come back to a human with a targeted question that will help it, just like an active student in the classroom, better understand the concept more quickly. Okay? So this is the active visual learning pipeline in general. And when we started looking at this, first we're checking out what is the traditional kind of pipeline or mold for active learning, and there are a variety of techniques. And let me just sketch one kind of cartoon example and then show you why it's not necessarily immediately relevant for our problem. Okay, so in traditional active learning, you have labeled data points. So let's say we've got cow images and non-cow images. Right? And if you were just to then survey all the unlabeled points, you might ask about the one that seems most uncertain given what you know so far. And say under this criterion, that's the one nearest to your current decision boundary. So you get that one labeled rather than any of the rest because you expect this to change your model most quickly, most efficiently. But notice a couple assumptions here. One, that this was a binary labeling task where I could ask a yes-no question and that would give me the information I need about the instance. Two, I'm also assuming in this sketch that any question that could be asked, meaning any point I might draw up, would take equal amount of effort for a human to respond to. But this is not the case when we're talking about learning visual object categories, right? So I can construct a yes-no question. So you can take these images and you could say, well, does it contain a phone or not? Okay, this is a yes-no question, but I could also ask someone more complex annotation questions, like will you outline the actual pixels to be even less ambiguous about where the object is in the image, or go so far as to outline all the parts, right? And at the same time, just as there's these sort of different levels of annotation or ways the human can communicate about the image content, they cost different amounts of effort as well, right? So generally what you see here is this trade-off between how explicit the labeling is versus how expensive it is. Okay. So our expectation is actually to learn most efficiently for a visual recognition system. It's going to require a mixture of these different strengths of labels. And we should be able to balance and acknowledge kind of the different costs that are associated with any labeling we might obtain. Okay. So the challenge is then for constructing the method is to be able to juggle these multiple levels of annotation, be aware of the cost or be cost sensitive, and to also, in the end, be able to push these jobs out to many annotators who might be working in parallel. Right? And these all present technical challenges in terms of the algorithm development to let us do active visual learning. Okay, so the first part about this that I wanted to show more specifically is how we can construct a function that will allow us to vary our choices of questions, not just the data points that we ask about. So what we want to do is create a decision theoretic function. So a function that will look at all of our instances and tell us which example should be annotated next and how should it be annotated. And at the same time, it should weigh the strength or the expected strength of this new annotation against the predicted costs that it's going to entail. Okay. So if I draw this in cartoon form, it looks something like this. So this is the view that I want the system to have as it's looking at all the unlabeled data. Right? So it would try to balance and look for cases where the information that's expected from an annotation we might get exceeds the effort that we think it's going to cost for a human to provide it. And so in these examples, you can see, well, maybe this image looks quite complex, but given our current models, it's not going to add much information. Whereas this one, which again is somewhat complex, there's a number of different objects in there, it's not necessarily going to be, or it is going to be very informative. So this would be a meaningful question to ask.
How is this related to the task of the vision system? So you showed these things, all the different levels of user annotation, but that has to be tied to the goal of the vision system as well. So some things just want yes or no, some things want other things.
That's right. So how does it tie to the task of the system? And here the task is to do region labeling into object categories. And so the kind of questions are, what is it and where is it? Yeah.
So you don't necessarily have to say exactly the boundary. It's just one point where it is.
Yeah. And I'm going to get to that in just 1 second, right? Because we could be asking a possible a menu of 3 questions in this case. Yeah. Come right back to this. All right, so in order to define this, I basically need to tell you two main things. One, how can we encode the labels that will have these different granularities, right? Because there is more explicit labels and less explicit labels. And that we'll handle with, we'll deal with first. And then I'll tell you how to design that function that will make this weighing between the cost and the information that's expected. So in order to handle these labels at different granularities, we make use of multiple instance learning, which you may or may not have seen. Basically, the idea is instead of just having positive and negative exemplars, we have bags of exemplars. And these bags are what allow us to encode label ambiguity. Because if we have a bag, say in the binary setting, if we know we have a positive bag, all that's telling us is that one or more of the instances in that bag are positive, but we don't know which ones and we don't know how many. Whereas if you have a negative bag, you know that these are negative instances. So the reason this is helpful in our scenario, now we have a way to represent, say, regions, which are specific instances with labels, as well as images that have only image-level labels, where we don't know which regions exactly are responsible for the class label itself. So if you think of that again in the case of images as bags of regions, say with an automatic segmentation, we might get things like this. And now we'll be able to say, if we're told that these images contain an apple, we just know that one or more of the regions contain the apple, and we don't know which ones. Right? Whereas if we're told that it doesn't have an apple, we know that all of these regions are negative instances for that class. Okay, and I'm describing this in the binary case, but just for visualization, but we can also do this in a multi-label case where all of these bags have multiple labels associated with them. There are various different techniques to solve multiple instance learning classifier objectives. We're using one that's based on a support vector machine-like objective with a kernel that will allow us to incorporate these bags of instances. OK, so now we have a way to express these labels of two different forms. Yeah, Adrian.
Are you assuming that the regions are now a priori?
We're assuming that we have an automatic segmentation. So those segments we know because we extracted them, but they're not necessarily perfect. So it's a bottom-up segmentation. OK, so we have MIL, multiple instance learning, to handle these different label granularities. And now I can define the 3 questions that are possible in this setting. Okay, and these are the questions that our active learner is going to be trading off as it surveys the unlabeled data. The first question would be, what is this region? Okay, and that would correspond in multiple instance learning. You're taking an instance and asking for a true label on it. Another kind of question would be, just tag an object in the image. And that would correspond to looking at one of these bags and providing one category label at the image level. And the third, and usually most expensive question to ask the human annotator, is to segment the image with the proper boundaries of the objects and also name all of those objects. Okay? So, okay. So we have these 3 different questions, and the picture to have is that as we iterate through this active learning loop, we're choosing which of these questions for which image will give us the most bang for our buck. So which one will have the most impact given the expense it takes the human annotator. So I can define a function then that this is where, this is where we'll be able to evaluate the quality or the expected value of information for some data object given some question. And we're going to look at this in terms of the current misclassification risk. So here this is saying we have some labeled data and unlabeled data. We could evaluate the current misclassification risk on that. And then we'll subtract the estimated risk if we were to get that candidate request, so to get that unlabeled object, O, and move it into the annotated set. Okay. So the expected risk reduction is basically our measure of the information gain. And then the cost of getting the answer is what will penalize that risk reduction by. Right? So again, just remember that bar chart where I was showing the information and the effort. Here, if you have a high reduction of misclassification risk, high information, and if you also have a high human cost involved, this term is high, and so these two will be weighed together. All right, and so to estimate this is very straightforward. To estimate the risk reduction, we have to make some prediction about how things would change were we to get the labels for those candidate points. And here, what we can do is look at the expected value over the risk according to all labeling. So here I'm just repeating this, which is the expected or estimated risk under the new model, where we have answered a question about this data object O. And so this is the sum over the risk, where we're taking the expected value over all possible answers. Okay, so think about cycling in your candidate unannotated image under the possible answers you might get, and then evaluating its probability of each answer, and then checking what the risk would be. Okay, so this is very easy to do for the first two questions I defined. So if we're asking for a label for a region, this has as many terms as there are labels in the multi-class setting. If we're asking for a label on an image, similarly. The more complex case is if we're trying to predict how is risk going to change once I get a full labeling of all objects in this image. Right? Because now notice that the label assignment is a joint label assignment among all regions. Let's say we have M regions in that image. Then we want to be able to predict how does misclassification risk change once I add all of them simultaneously. So we can't cycle over all possible joint assignments of the labels here, but we can show that we can use a form of Gibbs sampling to sample over these joint label assignments and use those as our expected risk reduction. Okay. All right. Okay, so this is how we're estimating the information, and then this last term for the cost of getting the answer. So here we need either some domain knowledge about the tasks that are at hand, or even better, we'd like to be able to predict the expense of a task. Okay, so what does this mean? Why would different tasks cost different amounts? Well, we already saw the example of whether I ask someone to get out a mouse and do this annotation, or if I just ask them to respond with a word, there's different costs involved. But in fact, it also varies per image. Right? So if I'm paying all of you to do annotations, which of these two do you rather annotate? You've got to do task number 3, which is full segmentation. Which one do you choose? The left. OK. And because it looks simpler, or do you know this because you counted the objects? Well, maybe it's both, right? So you know what's there, and you know how expensive that makes your task. But our intuition was that, in fact, there's generic complexity to the images, that even before the system is absolutely sure what's in the image, it should be able to predict the cost of some human getting out a mouse and drawing all the object boundaries. And this is kind of a similar telling example where I don't think you know these objects necessarily, but you would still have a preference, right? And so we wanted to capture this. So we wanted to be able to have this system running and just looking at unlabeled images and making its own example-specific estimates of cost. Okay. And in fact, you can think how this is not this idea of predicting the difficulty of the task is relevant not just for segmentation as we're handling here, but also things like the expertise that's required. So maybe I know people here in the second row are really good at annotating images that look like this. And if the system has this kind of targeted task generation, we can take this into account as well. Other things like the length of the video clip also is a strong indicator of cost. All right, so basically the idea here was to then learn how to predict this cost given the image content. Okay, so you learn a regression function, supervised way, watch people annotate images, time them. So here we're watching workers on Mechanical Turk, which is a service online where you can farm out some tasks and get them done through the web interface. So here's a labeling task. We're timing them. We watch many happy annotators, and we time them on these tasks. And then we learn a function where we can map image features like these, where here this is images, features that are meant to indicate the complexity of the image, so edge density at multiple scales, how fast colors are changing in local regions, things like this. And then we learn how to map these into predicted estimates of human time. Okay. So that means is now we have a function to plug into that last term in this selection to say, for this very example and the question you want to ask, how expensive is it going to be? So putting those together, we can complete this loop where, as we're making selections, what we're doing is saying, for all of these instances, how valuable do they seem to be? And then we'll bring back the most valuable one to the human annotator. And the two things to note about this technique relative to existing active learning work, one, we're targeting the question, not just the instance. And two, we're doing this with a predicted cost element. So traditionally, you would think of active learning curves where you look at quality versus number of iterations. But what these can kind of hide from you is the fact that if you ask a lot of expensive questions, you're overestimating the power of the responses that you got back. All right, so we're going to use this basic pipeline, and I'll show you an example result first with this MSRC dataset. These are multi-label images. They contain about 20 different object categories. And so there's multiple objects. So here we'd be interested in being able to label water, boat, sky, tree, maybe. And we use some general texture and color features. We get the thing going with some initialized set of image labels. And then we'll do this active learning loop between the 3 different annotation types and predict at test time what the labels are on the regions. Okay? So first, I'll show you the cost prediction outcomes. So just some examples here. So what we're looking at are data points of the actual time spent by the human annotator and the time we would have predicted they were going to spend on each of these images. So every point is an image. And you can see certainly we're getting some value out of this prediction. Here are a spectrum of simpler things that we think are simpler to things that we think are more complex. And we're right on these estimates. Here's one of our worst errors, this very fascinating patch of grass that to our edge features look complex. You can see kind of this is a possible pitfall of this unusual view. So we overestimate the expense. Here are a few more examples that take about equal time according to our system to annotate. And you can notice that different categories here we would still be predicting as taking similar amounts of time. Okay, so what that means is we're actually looking at the generic content of the complexity of the view. Okay, so we use these kind of predictions together with that misclassification risk reduction as we expect to find it. And using the active learning loop, here what I'm showing is kind of the key result, the kind of performance that we want to see at test time, where here as a function of the annotator effort, so how much user effort or how much money we've spent on annotations, the quality of the results on our new images. So accuracy, here you want to be high and steep in this curve so that you learn quickly with little human effort. And I'm showing 3 curves here. So the bottom one is random. This means passive learning. So if the system just will take whatever labels it gets. This is what I would consider traditional active learning, where it only can ask one kind of question. What is this? And we learn most quickly with our approach here in blue. And this is where we're juggling the different questions at every sequence or every iteration of the learning loop.
So, by random, do you mean that it picks randomly one type of label?
Right. So here it's picking at random the example and the question that it gets. Yeah. Yeah.
So you're paying more to have people label more complex things?
Right. So if we're having these on, if we're collecting these on Mechanical Turk, we would pay more for, as the market dictates, we pay more for the more expensive tasks. Yeah.
Okay.
Yeah.
And another question was, what are the features that make an image harder to label?
Right. So the idea behind our feature design was to capture things like how many boundaries are there. So certainly there's internal texture and so on, but if we capture at multiple scales how edgy is the image, this is suggesting how many objects might be present and probably a good cue for complexity. We also look at how fast color is changing for a similar reason. And when we do the learning, we're actually doing a multiple kernel learning, so we kind of gauge automatically which features we're selecting among those. Yeah. All right, so this is what we're calling multi-level active learning. And we're seeing that it's very powerful to be able to trade off the questions to get the most for the annotation expense that we can. But then we started thinking about this pipeline and realizing one practical weakness that we have here, and it's also a technical weakness in terms of the strength of the method, potentially, which is I don't just have one happy annotator sitting here. Right now the system is going in a loop, and every time we come back with a question, we get it answered, we come back and update the system or the classifier. But instead, I'd like to be able to work where I have many annotators working in parallel. Right? And what this means is the active selection shouldn't just be the best cost-effective instance at a time. It should be a batch of instances at a time, a batch of questions. So what we want to do is change this general loop. And instead of looking at the unlabeled data with our current model only, we'll also have an input which is the budget. Okay, so how much are we willing to spend at a given cycle of learning? And what we want to do is select the set of tasks that we could farm out in parallel such that we'd have the most advantage for improving our model. And if you think about this for a moment, it's challenging in terms of making a wise choice, because there can be, for one, information overlap between the choices you might make. So if we're simply ranking these and we get two similar things that we ask the question for, we're not using our money well. We also have to be able to account for still the variable cost among these different things, right? So if I want to come in with a budget, it might be that sometimes I ask a couple of very expensive questions at one iteration, at some other time I ask many cheaper questions. And this is exactly what I want the system to be choosing automatically. So I'm just going to give a sketch of our basic approach to do this, to do what we call budgeted batch selection. So we want to select the best set of instances that we should be getting labeled next, such that they're the best because they maximize some predicted gain over our current labeled and unlabeled data, and also maintain some budget. So each of these has an associated cost. We've already seen the example of segmentation effort as a cost here. And they have to meet the budget. So to evaluate this predicted gain, we're looking at two factors. So the idea is we want to think of the current snapshot of the labeled instances we have, here positive and negative green and red, and unlabeled in black. And we want to evaluate predicted gain in terms of the quality or how large the margin is, and what is our misclassification risk. Okay, so standard SVM objective terms. And what we're trying to predict is, OK, so should we choose some candidate selection? So say these were some candidate selection in this indicator S. And we were to suppose they're the best case scenario labels. So let's suppose that they were to have these labels. Then under that selection and that so-called optimistic labeling, how would the margin change and how would misclassification risk change? So what we do is pose this as a problem of selecting both the instances in the batch and their proposed labels in order to evaluate how this changes in a far-sighted way. So we're predicting the change to the model as these things are introduced jointly into the labeled set. So making this optimal selection is an integer programming problem in NP-hard. We show an efficient solution by making a relaxation to a continuous optimization problem. And we can efficiently iterate between essentially solving for the classified parameters and solving for the selection variables, right, that we'll use to introduce. Okay. All right, so this gives us a way to then go into that active learning loop with a budget in hand and make the best choices that will fit under that budget. And I wanted to show you one result using this technique for activity recognition. So here we're trying to learn these 8 different human actions from this benchmark Hollywood data set. And the task at test time is to say, does this clip contain action X or not? And so notice that this means that a natural cost for annotation is how long is the video? How long is the unlabeled video? Okay, because someone's going to have to watch it and tell us whether or not the action occurred. Okay, so we do this active learning loop. And what I'm showing you here are 3 different selections. Excuse me. Where if we were to just randomly spend our budget, we might ask someone to watch a very long video. Whereas if we use a myopic active batch selection, we might be choosing these examples. Excuse me. It's so exciting when I talk about this. I just get. Okay, so we might do a myopic active batch selection and just meet the budget with these less useful, maybe overlapping examples. And whereas our approach is looking to spend that budget maybe on some shorter clips that still are helpful to refine the current decision boundary. Okay, so imagine this happening at every iteration. We're making these kind of choices. So if we do this, and then I look at the results for those corresponding 3 methods, again, we have a passive method here in pink, and then that myopic active selection in batches versus ours. And again, this is still plotted as a function of annotation cost. Okay, So what this shows is we can spend the human time of watching these videos and giving us responses wisely, and more wisely if we consider, at selection time, their joint impact on the model. Yeah?
So if you look on this graph, myopic and random seems to be almost similar.
Yeah.
Does it say anything about all our active learning things what we have been working on? I mean, myopic is still kind of trying to use some kind of criteria to select.
Yeah.
Still, myopic does as good as random. Random is, I would think that random is going to be horrible. It's just not going to do anything at all.
Yeah.
So what do you have to say working on that?
So I think it's a really important observation, right? So these are doing similarly, and of course we can say, oh, well, in the far-sided, ours in blue is better, but you're right, the myopic is doing something intelligent, and yet it's not outperforming random here. But one thing to keep in mind is random is inflated versus its real-world performance here, I think, because if you think about the pool we have of data, it consists of things that are going to be relevant for learning this task, right? Because it's a Hollywood data set. Anything you pick and you get a label for is going to be relevant, right? And so this is something, in fact, leading very well to what I wanted to show you next. If we try to remove this kind of sandbox, right? So does the point make sense about this sandbox, right? So myopic active is doing something, random is doing quite well, and it has to do with kind of the limited data that's even there in the unlabeled pool. When in reality, we should have a much, much wider unlabeled pool. So this is what I wanted to discuss next, right? So we got kind of through this chain of results and these different techniques that we're developing, we get some confidence about the power, kind of the practical impact we can get for our annotation money if we use this kind of wise selection. But we're doing this so far, previously we were doing this in benchmark data sets, where maybe we're overestimating the quality or underestimating the quality of any of the examples. So the issues with this kind of approach, not only is anything relevant, but also the data pool is fairly small, and we know what's in it. And we can't help but know what's in it, we meaning the algorithm designers. It's possible these tests inflate the performance the estimates that one might make, and really we do have a researcher in the loop, and this goes for previous results in different domains, right? So if I'm thinking about posting Mechanical Turk jobs, if any of you have done this, you might find it's sort of a trial and error process. You think ahead about what's going to happen, and then you get some results, and then you come back and refine your interface to make sure, it's like whack-a-mole, like what errors are the annotators introducing next, and then I'll try to fix that. Okay, but that's really a researcher in the loop, and that's not what we want when we think human in the loop. We want our non-expert, possibly annotators, doing the jobs, but not the researcher in the loop. So the result I wanted to show you next is to look at a large-scale live learning problem. So here, we don't know what the pool contains at the onset. We're going to let the system crawl for images, which it can do with some keyword search and come up with candidates. And then we're going to pose an object detection task where we're going to evaluate it on a very difficult benchmark, the Pascal VOC challenge. And we'll make this scalable such that an unlabeled crawled pool can contain millions of examples. And this happens very quickly with detection, because if you think about it, you're trying to actively select which bounding boxes you might need a label for. Okay, so we have localization now, not just categorization. Right. So are you with me on this contrast between the sandbox, what I'm saying is a prepared data set, versus the live learning challenge? Okay. All right, so now I want to walk through how we accomplish this at the sort of the system level, and I'm not going to go into detail on some of the algorithm components that we needed to develop to get all of these pieces, but I want to give you this big picture, and I'll do it one at a time to sketch out this flowchart. So think about starting with a system that's crawling to learn about bicycles so that it can win the Pascal challenge and detect bicycles in new images. So we'll do some kind of keyword search, gather candidate unlabeled images. This would be the natural way one might normally start to collect a benchmark data set in the first place. And we'll have some initial annotations to learn the initial model. Okay, so from this model, we do something called jumping window prediction, which means we're using the the current model we have so far and extracting most probable unlabeled windows. So these images are just keyword search images, and then we have some windows, 2,000 of them per image, that we're focusing on for now. So this is our unlabeled pool. And then to make this scalable, we develop a new hashing technique. Okay, so backing up for a second. So an active learning criterion, and maybe even a good case, is linear time with respect to the unlabeled pool, which is actually quite expensive. Some are worse, quadratic, easy. But we can't afford to do this when this pool has millions or more examples in it. So what we have is a hashing technique where we can prepare a hash table containing all these unlabeled windows, where we've constructed it in such a way that we know when we come in with a new hyperplane as a query and hash that hyperplane, it's most likely to collide with unlabeled instances that are nearest to that current decision boundary. Okay? So instead of a point-to-point search, which we most often would do, here we have a hyperplane-to-point search. And that's like that simple margin criterion I defined early on. Okay, so this makes it scalable, because now if I know I'm mapping directly from the hyperplane to its nearest unlabeled instances, I don't have to apply that classifier to the entire unlabeled pool, which is unaffordable. I can go right to those that are good candidates for labeling. Okay? So we'll use this to then find out which things should be brought to our annotators in this live loop. Okay? So we bring them to Mechanical Turk workers. We get redundant responses, 20 of them, or sorry, 5 of them on each of these images that we bring back, and we expand this unlabeled annotated pool. All right, so there's a lot of diagrams on this slide now, but the main thing to notice is kind of this loop happening, and now happening on a very large scale in terms of data that's here, and happening completely autonomously. So once we press go, we have nothing to do with any of these results, right? Which is, of course, what we're always mimicking with our experiments here. I feel is really the real deal. So we're letting this run live, crawled data, and directly tying to the Mechanical Turk workers. Okay. So the key of this hashing component is the scalability. And so just to give you a sense, with these experiments we're running to learn categories from the Pascal collection, it takes us about 10 minutes to do an iteration to select 100 examples. Okay, if we were to do this naively, an exhaustive scan to accomplish the same thing, it would take 60 hours to do a single iteration.
What's the pre-processing to build the hash table?
So what's the pre-processing to build this hash table? So we have features extracted from the image, and then for every jumping window that's going to be entered into this hash table, we need to take some inner products between these instances. So what we have here is a locality-sensitive function that, just given an x, is going to be prepared to be sensitive for the inner product with the w. Yeah.
That's linear on the number. That's linear on the number of dimensions.
The preparation, that's right, yeah. So that one-time cost of getting those instances in there is linear, yeah. That's
that
right.
doesn't depend on the initial classifier, right?
That's right, right. And that's the key to make this appropriate, right? Because we can put all our data points in the table. They don't change. But the classifier does change over time. So what you can think of as querying with the hash function, querying with the classifier at every iteration. Yeah.
But the windows, it seemed, at least from the diagram, was coming from the classifier.
The windows were coming
From the classifier, or no?
well, they're influenced by it, right? Because we have the jumping window candidates, right, according to the classifier.
So the windows will not change as the classifier changes. You keep the windows constant.
Yeah, we know all these windows, all the possible windows that we're going to consider. We would hash into this table, yeah.
Oh, yeah, but so again, they are they are computed from the first classifier. Then?
That's right. Yeah, yeah,
I see.
yeah. Okay.
So this would rely on this would have to rely a lot on the first classifier. So my question is, so if you are trying to differentiate between, not between, say, bicycle and man, but between bird type A and bird type B, that consensus step right there will not be very decisive because you don't have expert labelers. So do you have some portion of this risk estimating the fact that your labels may be a little bit wrong?
Okay, yeah, so one thing just to clarify, when we get to consensus, it's consensus on spatial localization because here we're learning a category, bicycle, and then we'll give it to them and they say yes or no. So there actually, yeah, there could be two sources of label error if you think you see a bicycle or bird A and you don't, and also the localization. So here, this is our recovery for error, and we don't do more beyond this to say, you know, what did 5 people say, and then let's do mean shift on all their bounding box responses, and we'll get that back. But yeah, it's definitely there are accompanying issues in label agreement and things that you could bring into play here. Yeah. Okay, so we have this full system. It's running live. We have hands off, and we're going to try to improve state-of-the-art performance on the Pascal benchmark for detection. And what I'm showing you here are some sample images for those who haven't seen this data set. These are from 3 different categories. And you see they're quite natural scenes, very challenging to do object detection with these images. And what I'm showing here is a compact table that's listing those categories where we're making an improvement over the best results we found for this collection. These are among results from Pedro Falzenswab's detector and also some recent work by Vidaldi and colleagues. And so what we show here is that, in fact, setting this system loose, letting it start by knowing whatever we could learn from the Pascal training images, we can, in fact, see it improve performance for a number of different categories. And in some cases, these are significant gains.
Any idea about how much data was labeled during this process to get from that result to this?
Yeah, so we have more data than the previous best to do the training, and on the order of hundreds of images that are added. Yeah, and I'll show this in just one second.
So what if, excuse me,
yeah.
for those of us not familiar with the Pascal DOC categories, what are the numbers? That was 48.4.
Ah, right, yeah. So this is the mean average precision. Yeah, on the test images, according to a window search. Thanks.
Higher is better.
Higher is better. Yeah, that's right. Yeah, I'm missing a label. Thanks. Yeah.
What
Yes.
about negative examples? So you are actually using the word bicycle and then you're getting it.
Right.
Hopefully in Flickr, for example, most of them are probably correctly labeled, right?
Right, but there are some that don't have a bicycle or don't have one that would be acceptable as a training example. So if the answer is when we bring forth an image and say label this, if there's no bicycle, they say no. And we would treat it as a negative. Yeah.
There's totalization, right? So it's a pro-window thing, so you do get negative window.
Yeah, right. So actually there's there's slight disconnect here. So when you think of the active selection, you do have to think about windows. So you have more localized representation. But when we get annotation, we just present the image itself. Because it wouldn't make sense to present different windows when once they've seen it, they could just tell us. Yes, right, yeah. Yeah. But I'm just saying, rather than say, is this the dog, we'll just give the image and say, is there a dog? And if so, draw a box, yeah.
Result, you still implicitly have negative examples.
That's right, yeah. So even when we get a positive, we get more negatives. Yeah, and we do. We sample those maybe 100 windows around, yeah.
What I was saying was on Flickr, maybe people are more careful in labeling than, for example, just Google images.
Mm-hmm.
If you just type bicycle on Google, you get a lot more junk.
Well, in fact,
how does
those,
that sort of
yeah.
influence where you search for, right?
Yeah. So if you search on Google, you get different things. They tend to be more object-centric and maybe even more regular in the first ones. But it doesn't. The key is we're just using this as the initial unlabeled pool. In fact, you can think of it as just a very high-quality unlabeled pool, meaning this is kind of the state-of-the-art approach or the normal approach to build the data set would to do this kind of query, right? But now we're looking, even among those, can we make a better choice about which ones should be labeled? So which ones should we have a person actually prune rather than just take? Does that answer your question?
I'm trying to see that in any classifier you have to have this balance between positive and negative,
Mm-hmm.
otherwise you get biases and so on. So is there any effort to explicitly figure out?
Okay, right, and this goes to your point too, Marcel. Like once we get a positive, there's still the surrounding scene which serves as negatives to the object detector. Yeah. So you're worried that there's too many positives in the pool altogether, and that could be yeah.
What Marcel is saying, that if you have a very small object in this entire image, that's,
Yeah. Right.
So you have too many negatives.
Yeah. So we don't take all negative boxes. We take a sample of 100 boxes surrounding the one. Yeah.
If you want to use more negative, not more, because it's more jumping windows, I guess.
Mm-hmm.
If you will, imagine you were using a lot more.
Yeah.
100,000. For each image, if that were possible. Could you get away with a match with your classifier to start with?
More windows. Can you have more weaker classifier if you have more windows? In what sense?
Well, you have to start with some annotated data, right?
Mm-hmm.
The initial classifier to get the initial 2,000 windows.
Yeah.
Now, if you had a lot less annotated data at the beginning, you have weaker classifiers, so
Right,
you probably don't want to rely too much on those windows.
Yeah, right.
More windows, right? So would that work better? In other words, I could compensate with less annotated data at the beginning.
Yeah.
More jumping windows.
I think so, right, yeah. I mean, because in the extreme, we want all the windows, but we're doing jumping just to limit the total. But yeah, if you have a weak model to start and you know this, then upping the number of jumping windows, yeah, would help. Yeah.
So by that token, could you just start with a random, quantoid?
Yeah, that's the extreme, that's the extreme case.
A million, and then
Right.
a number of it.
Yeah, and I don't know the empirical answer for that because I don't think we haven't studied, if we just randomly initialize the windows, but yeah, it remains to be seen how bad it would be. Yeah. You can get a sense at some of these examples of how the difference and between what we get if we just do keyword search. So if you do Flickr keyword search for boat, you get the first ones you might randomly get someone to annotate look like this. And whereas the ones that we're going to pull up among all keyword Flickr boat images to get labeled next are the ones that are shown here. And these are the red boxes, are the boxes that we thought were closest to the current decision plane. Right. So the improvements that we're seeing is not just an issue of if we had access to the search engine to get more data. It's also that we selected the ones that a human should annotate among all of those possibilities, right? Yeah. So what's the upper bound if you took all the data that we collected and labeled it? You mean of all the unlabeled pool? So we don't have, I don't have this here, yeah.
Would that be the upper bound?
Upper bound in terms of for all data, what's your model quality? Yeah.
Well, not necessarily, because it could be that some positives actually make your performance worse, right? And in a way, by selecting the positives that are likely to make your model better, you are actually steering towards kind of better data. Maybe.
Right. It is true that if we label everything, it doesn't mean our test accuracy is higher. And these images kind of suggest this difference too, like Elios was saying, right, between boats that are probably going to adjust the model from where it is versus, we're not sure, but boat-related images that won't. Yeah.
But in the case of active learning, it's actually the other way around. You're trying to get the hard ones, and so you're kind of confusing your classifier more and more by getting the hard labels.
No, but it's hard ones in terms of doing better on a task, right? So they are in a way useful ones too.
Yes,
right?
but and what I'm saying is it's not sure either way.
It's not sure, yeah.
Either way, it's not sure.
But so Dave Ramanan had this example where he, I think, doubled or no, 10 times more data for Pascal, and he didn't get really much better performance.
Okay.
So this suggests that just adding more data by itself, it's not clear whether that actually.
Right.
So that's interesting to see. I think it would be a really interesting thing to see whether getting more data will actually kind of indiscriminately will get the numbers down.
Right. Yeah, and I mean, it's kind of revealed in these sort of results, right? These are more learning curves where if you're just to add more data in a random order from the keyword search in red versus if you do it actively in blue. And so we can see this, I think, an effect related to what you're talking about, right?
I mean, the interesting thing would be what happens at the limit, kind of, as you go more right. Are the two curves going to join up, or are they going to keep being joined? That would be interesting.
Do you have any insights on why chair is?
Yeah, why is chair so bad? This one, yeah. I think chair is the quintessential difficult object to recognize. Yeah, one of them. Yeah, here keyword search is stronger than our approach. Yeah. I mean, if you look at the variety of the images, actually many classes have some extreme variety. Maybe chair is a bit more than the others. Yeah.
What's the difference between keyword plus image and keyword plus image?
right? So keyword plus image means randomly choose an image you got from keyword search and get it annotated with the bounding box if there is one. Keyword plus window means look at all jumping windows and randomly choose one of those to get labeled. So it's a weaker baseline. Yeah?
So I was going to save it to the end, but since the chair question is, I'm curious about your cultural sensitivity to the humans who do the classification. All the classes that you show are simple nouns.
Okay.
But if I have classes like delicious and friendly, half the world would put dogs in one class and half in the other class.
Hopefully not half. Yeah.
If you have a random sampling.
Okay. Yeah. Okay. So,
What do you think about it?
yeah. So what if our task is not so universally agreed upon names of objects, but it's something else with, yeah. So yeah, I think here again it gets to a challenge that was raised about dealing with the agreement. And here my task is a categorization task. And I think that people, they aren't expert trained, but they know how to answer these questions. But I mean, I agree it's an interesting challenge. I mean, one thing we've tried to do that we quickly abandoned that gets to your point is we wanted opinions on how a retrieval algorithm we had developed was doing. And we didn't want the 10 opinions of people in the lab. We wanted hundreds or thousands of Mechanical Turk opinions. But there we have kind of, you know, how do you verify the quality of the response? And it is subjective, and you have these differences. Yeah. Yeah, it's you know, some things you can package for crowdsourcing like this, and many others you may not be able to so well. Yeah. Yes.
Is it possible to use the segmentation for rather than those jumping box?
So if we use regions instead of a jumping window.
Yes.
Perhaps. Yeah. So depending on our detector representation.
Yes. If there are a bunch of segmentations, would that be good or bad?
Yeah, again, I think it matters. It depends on what our representation is for the detector. Here we have some sparse coding max pooling within the pyramid of windows, so kind of a texture, local feature representation. But maybe if we were trying to get more of a shape representation, we would choose to use regions instead. Yeah, it's possible. Okay. Okay, so there's one more piece I wanted to show you. I'm going to keep it very short and sweet. Just to give you a sense of how, instead of asking these questions, we can listen more to the annotators. And this was the second part, but I'm just going to give you the main idea. And the idea is, how do we listen more carefully to what people say in the way that they respond or describe an image? And so certainly we can think, you know, of these flicker kinds of images. The words are telling us what objects might be there. Some of them are present if they're mentioned. And there has been a great deal of work to look at ways to discover what are the correspondences, which things really are the object that are named, where are they in the image. But our idea was that there's more in these tags than just which objects are present. Right? So when someone gives you this list of keywords and you get them in order, there's some more information there beyond just what's in it. And kind of a telling example is this test for you. So here are 2 hidden images and 2 lists of keywords, tags, that someone gave, one for this image and one list for this image. And what can you say about the mug that's in either of these images? So I'm hiding the images, but what would it look like?
More prominent than the other, different size.
Yeah, more prominent, different size, and probably this guy is more central, maybe larger, right? And that's true. So what we wanted to do is basically capture these implicit localization cues from the way people react or describe these images. And so what we do is create cues from tagged images for which we know where the object is and build a localization prior over those tag features. And the tag features include things like what order are the relative words, what's the mutual proximity between any of these words, because we know that people will look at an image and notice something and then maybe look at some other things nearby. And also which words are present or absent. So we define these all as implicit tag features and learn this localization prior using them, so that now when you get a new image, you can also look for the object in normal ways with a good object detector, but also trust certain locations more or know where to look first because you have these implicit localization priors. Okay? And so if we do this, we have a system now that if we give it an image with tags, we just look at the tags, and already we have a guess of, say, the top most likely scales and positions for some object of interest. Here it's car. So before seeing the image, here's our guesses of where the car might be. And then we will look at the image, and you can see often we're getting a good estimate to start looking. Here's a failure case because the car is maybe somewhat unusual. It was mentioned with just a very short list of words, and we guess wrong for our first guess. Okay. So that's kind of the very brief version of this idea, how you can use some implicit information about some annotations that humans have given. And we've used this to speed up detection so we know where to look first for the object. And we also use it to refine the accuracy of a detector. So imagine doing total sliding window search on this image, but then adjusting your estimates according to appearance using these tag features. So all of a sudden, this looks less like a mug because of where it is or how big it is, and this looks more like a mug. Okay. And I'll show you a sample result. So here, again, we're working with some Pascal images to do detection. And we have keywords or tags collected from hundreds of Mechanical Turk workers. Usually every image, we don't put a limit on it, but they'll usually give us about 5 words for every image. And here what we see is that we can improve the speed of the detector. So relative to a sliding window search, we're getting similar for the same detection accuracy. So this is accuracy here. We search much fewer windows. And we improve that metric from before, the average precision. Okay, so finally, I'll just show you some qualitative examples for this. So these are Pascal images. And what I'm showing in green is our most likely localization for the object. Here, bottle and car. And in red is the localization estimate from the detector alone. So this is Pedro Feldenstaub and colleagues' latent SVM detector. And you can see, given this list and kind of the perceived importance of the different objects and that connection to scale, we make some better first estimates for these examples. More cases, ours again are in green, and the baseline is in red. Okay, and of course, this doesn't always work. And here are some failure cases where, perhaps due to the unusual nature of the scene, so we haven't normally seen buildings mentioned with airplanes in this kind of view, we'll make an incorrect best estimate for the object. Okay. And we've gone further on this direction. We looked at how do you remove the requirement that your input image even have tags. So we can learn this connection between the implicit localization cues and the visual content, and learn some projection from either modality, either the words and their importance or the visual features, such that things are close if they originated from the same instance. And that'll allow us to then come in with a new untagged image and be able to estimate which images are most like it in terms of the important objects, or the kind of objects that someone might describe first if looking at the view. And here's one example result doing that. If you were to look only at the visual content, this query is pretty well matched to all of these. If you were to learn a representation paying attention to words as well, you can find some with some overlapping words in them. But finally, if you use our method, what we want is to come up with the images that are related in terms of total content, but also share the same prominent object. Okay. So just to recap, what I've shown you are our recent work and how to more effectively transfer human insight into these visual learners. And we're largely looking at this as an active annotation problem to figure out what questions to ask. And I talked about some of those technical challenges of varying the question, of coming up with batches of questions at once, and how to make this scalable for millions of examples. And then finally, kind of in a slightly different way, we're looking at how to get more from the kind of things that people tell us, maybe without even knowing that they're telling us this extra information. Okay. And thanks for your attention. If there are more questions, I'm glad to take them.
All right, questions? Let me start. So I was looking at your kind of the story, and you are really explored very well the idea of what can we get from these. How can we figure out what how to use the users best? But the type of labelings themselves, except for I guess a little bit in the last part, the type of labelings themselves were still very much kind of a standard. Either we outline the bounding box or the segmentation or maybe something. But it seems like your framework is perfectly designed to actually test other ways of labeling that we haven't even thought of before. For example, you don't care to label all of a dog. Maybe just the muzzle of a dog is enough to improve performance, right? I guess this last part is a little bit on that in terms of tags, but in the terms of images, you might also, have you looked at kind of thinking what could be kind of new ways of labeling that maximize value, minimizing the cost?
Yeah, sure. So what I've shown are just a handful of examples, and you're right, there are other ways to expand your questions or label spaces, and many of them are possible to work into this as long as we can still estimate posteriors and so on and compute these criteria. So a couple that we have looked at beyond the ones I'm showing you here, things like attribute naming. So if I have visual properties that are attributes, things that are shared across different objects, it might be wise to be asking questions about those alongside the objects themselves.
And what the results there are? Are you getting better with the attributes than the segmentations or not?
Right. So what we're studying is whether interspersing these kind of attribute questions can allow us to learn more quickly than if we only care about the object labels that we want to predict. And we're seeing some good results there. That's what I mentioned. I mean, you mentioned localizing apart. I mean, it's possible. We haven't looked in this paradigm yet. So, yeah. I hope that by suggesting these basic tools, I mean, if there are ways to use the annotation of interest in your problem, you can use some of these basic tools to do that.
Right,
yeah.
right. The nice thing is that now you're not forced to do these standard things. You can basically play around with new things, and it will just work in the same framework. Yeah.
Yes. So I have a question about the second part of the talk. So you have a model that you want to learn, and you say, well, if I have an estimation of how much is going to cost me to label this image, I can intelligently choose which images and which questions to ask which one of the images. And for that, you see that first you train, you have to learn this function that tells you the expected cost of each one of the images. So how do we know that you're not just trespassing the cost that you're saving in the first system into what you're paying for training this other second system that you're using for improving the first one?
I see. So you're saying maybe I spend enough money learning how to predict cost, then I'm going to save when I use the system online.
It looks to me that it looks like one of those programs that can be learned online and simultaneously, like sort of I don't know, minimizing the regret. Where you have to both estimate how much it's going to cost you to label the image at the same time to choose which images to label.
That's right. Right. So if we put human time and machine time more on equal footing or something like this, right?
So I don't know if we've done anything.
Yeah. So we haven't looked at measuring those simultaneously in such an explicit way, like in the VOI function itself. But the work I was presenting on the live learning is where we're getting quite serious about the machine time and thinking, it's not okay to go offline for hours and decide what question to ask, but we have to become basically online live, be feeding these jobs out quickly. Yeah, but it's a very interesting kind of just another factor right in this balance that you're trying to do, and for your setting, which ones are most important could inform how you design it. Yeah.
Questions? Oh, sorry. Yes.
So I had a question about the first part of your talk. So the coupling between the prediction of how good an annotation will be and the task that you want to do. So obviously, the more the more fine-tuned the prediction is for your task, the better it's going to do, right? On the other hand, you don't want to like before you have all your annotated data, you may not want to design your algorithm before that. So how closely coupled does the prediction have to be to the task that you're doing?
Okay, so how closely coupled is the cost prediction function design, or even the features for that?
Right, like you chose these edges, right?
Right.
Which were somewhat generic, but the more closely tuned they were to your task, the better the prediction would presumably do, right?
Right.
So there's kind of like a balance in which you have completely generic features, which wouldn't be which would do as good for a particular task, as opposed to having very fine-tuned features, and then your reusability of your annotations will be very low. So is there any sense that you have on how well coupled they are?
Yeah, I mean, I think you're right that it is, that particular part is coupled and needs to be, right, in terms of the cost prediction. I mean, I can't expect to learn in a supervised way any effort function just given the features. But this one is well suited because it's something about the image that's generic. So yeah, whether it's possible to plug in an arbitrary efforts and learn it in this kind of way from watching people do the task, yeah, I do think coupling seems necessary, yeah. I don't know if there's a task in mind that you have, but just, yeah.
Okay, so I think our dear speaker is almost out of time to go to the airport, so I think we should finish up then. There is a PSR already started, right? So maybe as we chaperone our speaker, we can maybe force feed her something before her flight. You guys can ask more questions. Let's think again, Kristen.